Okay, so I'm going to get started. So we talked already about the sort of the core architecture of the overall compiler technology. We talked as well about the extensible class mechanism that we use to architect the structure of a lot of the classes within the compiler technology. And as we're looking at implementing a 64-bit code generator, I think that what I wanted to do is to go through some of the various aspects of the code generator technology and make sure that everyone is sort of aware of what their purpose is and the kinds of changes that we would need to make in order to implement a 64-bit code generator. So so there's about 13 or 14 sort of concepts that I wanted to go through. These are by no means an exhaustive list of all the things that we have to go through, but it's also not the most, it's not the deepest sort of explanation of what the purpose of all these different pieces are for and what they actually do. What you'll find once you start getting into some of these classes is that the purpose of some of these components is a little bit blurred in some cases. They tend to do more than what they appear to be responsible for. That's not necessarily a good thing, and it is something that we, as the Eclipse OMR compiler community, want to sort of remedy over time, and it's sort of an effort that we have on improving what we call the conceptual integrity of all these different components. But I'll try to keep it as straightforward as possible. Okay, so the main sort of body of work that where a lot of the effort has to be concentrated for this particular effort is in the code generator class. The code generator class is you can think of it as multiple levels. There actually is quite a bit of stuff that occurs at the architecture neutral layer. So this is things that are sort of sitting way up at the base OMR layer. This is an extensible class, by the way. But there is also a fair bit of specialization that occurs for each architecture that we're dealing with, and that's actually to be expected. So the main purpose of the code generator class is to be sort of the overall orchestrator for taking IL and then turning it into machine instructions that can ultimately be executed on the target architecture. As I said, it really inherits a lot of functionality from the class above it. If you go and look at OMR code in the CodeGen directory, codegen/OMR codegenerator.hpp, you'll see that it's got an awful lot of functions in there. There is sort of some comments in there that try to carve that up into different sort of sets of tasks. So, for example, things to do with register assignment, things to answer questions about capabilities, things to do with global register assignment, things to do with tree evaluation, that sort of thing. There's data structures and all kinds of things under there. So you get a sort of a rough sense of that. As I said before, I think that a lot of this actually can get cleaned up, and it should be cleaned up to make the real purpose of the code generator much, much crisper. But as it is right now, it's not quite that way. It's really responsible for driving the code generation phases that have been specialized for a particular architecture. So the main ones here are instruction selection, so the translation of IL into instructions, local register assignment, and binary encoding. So taking assigned instructions and turning them into the appropriate binary encoding that's appropriate for a particular architecture. It also does things like answering questions about what a code generator is capable of doing. So the example I've got here is you can ask, like an optimizer can ask the code generator if the code generator is capable of doing something optimized for square roots, and in some cases it would leave it alone, not optimize it, knowing that the back end is going to take care of it. And another big thing that it does is it really stores a lot of information that's needed during the code generation process. All the different phases that occur during code generation, you can sort of think of all of those together as one big process. And sometimes there needs to be information that flows between them, and we need to store that somewhere. And the right place for that is the code generator. So, for example, maintaining the stream of instructions that it's working on, or maintaining the list of all the virtual registers that have been created so far, or the live list of registers, things like that. So there's lots of data that needs to be collected and represented as instructions are generated. At any time during this talk, by all means, interrupt me if you can and ask a question. Otherwise, I'll just sort of keep plowing forward here. Another important class is the machine class, and its real purpose is to provide an architectural description of the register file. So what registers are available on a particular processor, and how do you kind of go about manipulating and using those registers. So it also contains things to do with register assignment. So how do you choose the best? So during register assignment, the question is going to be asked when you're coming upon, when you have to assign a register to an instruction, what is the best register to assign at this point? And the way that things are implemented is that the machine class, contains a method that basically answers that question. If you find that you need to assign a particular machine register, but that register is already taken, you need to have a mechanism for freeing that register, and that's also the responsibility of this class. And if the time comes when you don't have enough registers and you actually have to spill some of those to memory, this class is sort of responsible for managing that as well. It does a few other things as well to do with register assignment, but those are really sort of the main operations that it has to take care of. The other thing that it does is the different register there are multiple register assigners that are available. There are global register assigners and there are local register assigners. This particular class is responsible for answering the questions that those register assigners might ask about how many registers are available and what the ranges are and that sort of thing. So it's usually provided in a table form. So that's it for the machine class. I guess one thing I should have mentioned here as well is that what it also maintains this fairly large table called the register file that really describes each of the real registers that are available and what their properties are and whether or not they're available for assignment and that sort of thing. So you would find that in this class too. Okay, excuse me. So the next two slides actually you've already seen before. And so I guess that you just sort of consider them to be a recap. So the PreEvaluation is a fairly important phase in the code generator. And it actually involves a number of different little steps, but the real objective of PreEvaluation is to really produce native instructions for various IL trees. We call that instruction selection. And what we're really doing is flattening a tree into a stream of instructions. And the word evaluate, when we use that word, what we really mean is that we're generating instructions that when you execute those instructions, it's going to cause the value of the tree that you're evaluating to appear in a virtual register. And the act of tree evaluation, it doesn't care about, it doesn't have any notion of a limited set of registers. It really just uses whatever virtual registers are needed. And the assumption is that register assignment, real register assignment later is going to come along and make sure that the limited set of real registers available on an architecture are going to map onto that onto that infinite set. Excuse me, having trouble talking tonight. So if a node produces a result that's consumed by other nodes, then that virtual register is going to represent that result. So I think I just said that. So, okay. So the way that the nodes are generally evaluated is that the children go first. We do a recursive post-order traversal. I showed an example of that in the presentation a couple of weeks back. Then once a virtual register is produced, you sort of set that register on the node, and then that register really becomes the value, represents the value of that node. And the whole thing is sort of guided by these reference counts. So how many times have you seen a particular node in the trees? And it really gives you a strong indication of how to make register decisions. So, for example, if I know that I'm on that the reference count on a particular node is 1, I know that this is the last and only reference of a node, so I can make decisions about the register itself. Like, for example, the register I know will go dead after this point because the reference count is 1. So anyway, I didn't want to go into too much detail about that again, but I just sort of wanted to actually reintroduce the terminology of evaluators, because each node, each IL opcode actually has to have an evaluator, and an evaluator again is something that'll take that opcode and turn it into a sequence of instructions. And every code generator is responsible for providing evaluators for all those opcodes. It's very, very unlikely that any code generator is going to share an evaluator with another code generator. They're that specialized to that particular architecture. And I think, as we'll see when we start looking at ARM64, this is really where the bulk of the work is going to be in producing these evaluators. And some evaluators are fairly trivial. Others can actually get fairly complicated, like, for example, with calls and that sort of thing. So just to give you sort of a quick tour of what kinds of evaluators there are and where they generally live in the different code generators. There's a file called PreEvaluator, a class called PreEvaluator as well. It really contains a lot of a very general, generic node evaluator. So, for example, things like BB starts or, some fairly simple nodes as well. Control flow evaluator really contains the things that have, anytime you're evaluating something that will generate a branch or some kind of control flow, this is typically where it ends up. So it contains things like ifs, branches, if you've got switch statements, if you've got things that generate or can throw exceptions, you've got go-tos, that kind of stuff. They all sort of live in the control flow evaluator. I should point out that for any of these evaluators, it's really just sort of a logical classification of these things. There's no special properties or special powers that something gets by being in one file or another. It's just a matter of grouping them together. And it's really just to help you, as you're sort of navigating around the code base, where to look for a particular evaluator. FP tree evaluator typically contains floating points evaluation code, so we tend to stick it all in there. Binary evaluator contains evaluators for binary operators, so adds, subtracts, multiplies, that sort of thing. There typically is a unary evaluator as well. I don't list it here, but there's usually a unary evaluator for things like negation and other sort of operations that deal with that. And then there is sort of a helper class that is available that helps you generate the most efficient code for a particular architecture. And you typically write this per architecture, but what it does is it sort of analyzes, so in the case of a binary commutative analyzer, it analyzes commutative operators, so things like adds or multiplies, and it looks at what is the best way of generating an instruction for a particular operation. So, it understands that, I don't have to load this particular parameter because I have a register memory form, and this is the last and this is the only reference of that load, so I know I don't need to put it into a register, so I can basically use the register memory form directly. Or it knows that, well, there's actually a reverse form of this instruction, so I can actually reverse the children because it's a commutative operation, and I'll get better encoding that way. So depending on the architecture, there's lots of things that can actually happen in here as well. So we'll have to look into encoding something like that too. So one of the key building blocks of the output from the code generator is our instructions. So this is actually a fairly interesting hierarchy. And so what it is, what they are, it's basically a dynamically polymorphic hierarchy, but the base class of all the instructions is really an extensible class. So what we've done is we create a TR instruction concrete class that contains basically functionality that all instructions in OMR use, and it's specialized by the target architecture and your particular language runtime. So in the case of Java, if you're working on something for Java, Java can actually provide in this base class its own sort of specializations. And then basically what that forms is a TR instruction base class. And then a particular code generator can come along and create instruction kinds that really derive from that base class. And those are actually dynamically polymorphic. So I'm not actually 100% familiar with what's going on right now in ARM, but from an x86 point of view, from which I have much more experience with, you would derive, for example, a single register form instruction from the base class. And then from there, you could derive a double register form, so a register form from that. And then if you actually had a double register form with an immediate value, you would derive from the register form a register immediate form. So you're really building up this hierarchy based on instruction kinds, and it's really, again, dependent on whatever the architecture is that you're working with and what its capabilities are. So we'll have to see what makes the most sense for A64 here. So each of these instructions, they're actually strung together in a doubly linked list, and this really forms the instruction stream. There's actually two kinds of instruction streams. We have like a mainline inline stream, and then we've got an out-of-line stream, and I'll talk about the out-of-line stream a little bit later. But for all intents and purposes, when you're actually creating and evaluating nodes, you're actually evaluating them to this inline stream. The identity of a particular instruction is further refined by associating an instruction opcode with it. So, for example, in the case of a single register form instruction, there could be multiple nodes there could be multiple opcodes that can be associated with that. Like, for example, it could be a negation, or it could be, let's say, a push form, or like a push opcode, or something like that. The other responsibility of the instruction, of a particular instruction kind, is that it really needs to orchestrate the register assignment for that instruction and the binary encoding of that. Most code generators in OMR right now follow this kind of model. Something like the Z code generator, though, they tend to do things a little bit differently there. They've actually gone and, they can have register assignment that works on all, like they have a single path, a single set of functions that work on all the different kinds of instructions. So you will see that there's a fair bit of redundancy if you don't do it that way. So the way that they've done it on Z is actually does tend to save on the logic and commons up some of the redundancies that would be present. But we have to think about if we wanted to kind of go that route as well. But for now, the basic way of doing it is to actually have each instruction take care of its own register assignment and binary encoding. Okay, so the opcodes. So the opcode really describes the function of an instruction, and it is often mapped to a real processor instruction, so an add or a multiply or divide, something like that, or a call. But it can also be mapped to a pseudo instruction. So these are things that don't really escape out into the, like won't actually get binary encoded, but they have special meaning in the instruction stream. So you can, so some of the things, some of the metadata you can associate with an instruction opcode, they all have properties. So, you know, answer questions like, is this a branch op? Is it a record form? They all have, if they're a real instruction, they will actually have a binary representation. And then they also have some printable mnemonics that are used when you're writing out to log files and stuff like that. So anytime that you're describing an instruction opcode, you're going to have to provide all of these different things. Now, I mentioned pseudo instructions. So what these really are just placeholders, or they are macro instructions. So some examples of these would be a label, right? So in your instruction stream, if you want to be able to provide a target to branch to, you would create a label symbol that's associated with a label instruction, and then you can branch to that. You can create a branch that goes to that label, or things for describing the basic block entry or the entire procedure entry, or in the case of a macro instruction, and in the case of Java, you could have something like a write barrier instruction that what'll tend to happen with the write barrier instruction is that they tend to have a lot of logic associated with it. So in order not to pollute the trees or the instruction stream too early, you know, we basically use a compound write barrier pseudo instruction that gets expanded out later. And much of the information that's associated with a particular opcode is actually in a table format. And what that means is that you'll find that there's a big, massive property table, usually that's indexed by the opcode. Binary encoding is the same way. There's like a binary representation table that gets indexed by the opcode, and same thing with the names of these different things. Now, the generation of these tables is really depends on the code generator. Some of them, like x86, for example, will generate them by hand. At one point, Power and Z actually used a tool to generate these tables, but that is not the case anymore. These tables are actually maintained manually. And I certainly think that when I talked about conceptual integrity, I think that one of the future things to do with instruction opcodes across the different code generators is to really come up with a common solution for generating these tables and making it as easy as possible. And probably using some kind of a tool to do this would be the best thing to do. But at this point, most of the code generators actually have to use, and probably ARM is in that boat as well, generates these tables manually. So it's a bit of a pain, but that's just the way that it is for now, unfortunately. Okay, so one of the components of an instruction often is some kind of an addressing expression, or sorry, not an addressing operand. And the representation of an addressing mode on a target processor can be achieved through a memory reference. And this is typically very, very specialized to a particular processor architecture because the addressing modes on those different processors are typically different. So just an example of what a addressing mode might look like, you could have a form of an instruction of an addressing mode that has a base address plus some stride times an index plus some displacement. And you would use that form, for example, when you're indexing into a linear array or a linear piece of memory, right? So Depending on the architecture, you're going to find different addressing modes, and therefore the memory references are all going to be different. So what we need to do is to sort of figure out what makes the most sense for AR64, and come up with the right sort of memory reference representations for that. The other thing that the memory reference is responsible for is for orchestrating the evaluation of a node, and of a node that operates on memory. So, for example, some kind of a load, or perhaps even a store. And by providing that kind of evaluator, it'll produce a memory reference that you can hang on another instruction that's in a very correct form, and perhaps more importantly, the most efficient form of addressing mode for that particular kind of evaluation. So you'll see, if you look across all the memory references on all the different architectures, that they have a form where I think it's called, and they've all used the same name. I believe it's populate memory reference. And you basically pass it a node, and it does sort of a recursive walk down that node, and it'll actually go and produce the most efficient memory reference for that particular kind of addressing expression you're trying to do there. And then you take this memory reference, and where it's really only used is as the operand of an instruction. I can't really think of anything off the top of my head where a memory reference is not used in any other context than an operand to an instruction. And again, it understands for a particular architecture the requirements for forming an addressing mode, and the limitations of that addressing mode as well. And when I say limitations, I mean things like, if in some architecture and you're doing some kind of a base plus displacement form, there might be a rule, for example, that the base register always has to be GR2 or something like that. So that's the kind of thing that a memory reference would know when it's actually getting encoded. And the memory reference also has to be able to do register assignment and to encode itself, understand how it needs to get encoded in instruction forms. Register is another important component of instructions, like as an operand for an instruction. So the main concrete representation is a TR register extensible class. So the TR register base class really represents two different things. So it's basically it's basically the root of the whole register hierarchy that you might want to build from, but it also represents these pseudo virtual registers that we've been talking about. So it's a register that doesn't necessarily it isn't a real machine register. It's an artifact of the evaluation process. So it is a bit overloaded there. As it says here, it's an abstract representation of a machine register. They can have different kinds. So, for example, this is a general purpose register. This is a floating point register. This is a condition code register, that sort of thing. If you look in, I'm trying to remember where that is. I think it's in register constants and CodeGen register constants.hpp. That will sort of give you a very large enum of what the various kinds are that are available. There's actually more than you might think in there, and I think that came about from when we added vector opcodes and things like that as well. So and other purposes as well. So anyhow, the most common ones for sure are the GPRs and the FPRs, and if you've got condition code registers, it'll be CCRs too. The base class also sort of maintains a notion of the number of times a register is used in the instruction stream, and as it's important for register assignment, it needs to know as it's going through and doing assignment how many more registers are coming up, because it needs to know when it gets to the last use of a register, and therefore that register is now dead, and important things can happen from that. The base class also maintains the backing storage. So backing storage is sort of a very old IBM term for basically still space for a register. So when a register cannot be represented in a register, a value can't be represented in a register, it has to be stored somewhere. And we store it, that's basically a spill, and the place that we end up storing it is what we call backing storage. But what it really is it's just a slot on the stack of the method that we're compiling, and that's where it's going to live until it gets resurrected again. It also has a link to, for example, if it actually is assigned to a real register, it's going to have a link to that real register in this base class too. Right. So once you have this base class, you can actually start to derive things from it, like dynamically polymorphic things from it. So, for example, a real register is really just a specialization of this base class, and what the real register is, it's just a representation of a real register on a target, right? So this represents GPR 8, right? It represents something like that. But it also knows things about that are important for register assignment. So it knows its state. I know that it's assigned, or I know that it's been spilled out or locked or freed or unlatched. And at some point we can probably talk about register assignment in more detail, but I guess I'll just quickly go through what those different states actually mean, since I just mentioned them here. For a real register to be assigned, it means that it actually is assigned to some virtual register currently, like it is actually being used. Spilled means that a real register is, actually let me think about that one, because I don't quite recall what the context is in the context of a real register, what that actually means. Locked means you cannot use that real register for assignment under nearly any circumstance. Free means it's available, and unlatched is sort of a special state of a register that is used on instructions that have got multiple registers, it's possible that a register can actually become free in the middle of an instruction, right? So if you know that this instruction is actually going to kill a register, that register is going to die there. As soon as you assign that part of the instruction, like that, let's say the target part, it'll now become free, and then it could potentially be used in the source part of the register as well, as you go through and assign those. So we can go into those in a little bit more cogent detail when I talk about register assignment in the future. Register pair is another kind of abstraction and a specialization from TR register, and it's really just an aggregate of two TR registers, and it's really a way of associating two of them together. And it's really useful when, for example, you have, so let's say on 32-bit architecture, and you want to represent an 64-bit value. And the way that you can do that is by associating two 32-bit registers together that represent that 64-bit value. And the way that you ensure that those two 32-bit halves are considered together is with a register pair. I believe that there's also some uses of this on some floating point architectures as well. I'm not quite familiar with that, but that really is another possible use of this. Okay, so register dependencies are a little bit different as well. And so register dependencies are really the means by which specific real registers requirements are enforced on a register that's used in an instruction, right? So this is where you can tell, where you can basically specify that if I'm using this particular instruction and this instruction expects that the shift length is going to be in a certain register, right? Like it's going to be in like GR0. then this is the mechanism that you use to enforce that. So what you're really doing is you're telling the register assigner, these are the conditions that must be true, like before and after you assign the registers for this instruction. So we've got the notion of preconditions, so sort of the state that has to happen before the instruction, and then postconditions, the state that must be true after an instruction. And typically every instruction, this is true I know it's true in x86 and Z. I'm not 100% sure if it's true in Power and ARM yet, but almost every instruction you can hang a register dependency on. I think Power still uses dep form instructions. Like you actually have to have a specialized instruction form that you can hang a register dependency on. But anyhow, there should be a form that you can find where you can hang a register dependency on if you need it. And the way these actually look is you basically, it's sort of a mapping of a virtual register to a real register, right? So, GPR 836 has to be assigned to has to be assigned to GR0, right, in the real register. And you can really sort of build up these sort of mappings of that. But we also have some sort of special pseudo-real registers that you can use as well. So I've got two of them here, so probably the most common ones here. So you can also specify what's called a no-reg dependence. And what you're saying is that I have some virtual, let's say GPR 396, and I don't really care what real register you give it. Just find it a real register and make sure that it's assigned at this point. And why you might think, you may be wondering why that's even useful at all. But there are some circumstances in the code generator where you have to carefully manage the spill state of a register. And the biggest example I'll give you here, and it's something we're going to have to watch out for as we start doing a lot of these evaluators, is that the biggest assumption in the code in the back end is that you don't introduce control flow. Right. If you start introducing branches in that, the local register assigner on any architecture doesn't know anything about control flow. It can't follow. It can't maintain. It doesn't know that, okay, this register was spilled on this path, but it's not spilled on that path, and it cannot maintain that state at all. So the way that we kind of get around that is by managing that spill state yourself. And the way that we do that is with these sort of no-reg dependencies. Byte-reg is sort of it's kind of similar to that in that when you're in some architectures, you can't represent byte registers. You can't do byte operations on every register. So you actually have to ask for a register that is capable of participating in byte operations, right? So that is useful. And really where register dependencies are used a lot are in enforcing the linkage and, as I said, and controlling spilling. So I think we're going to be talking about linkage next, but really it's, yeah, well, let's see for that. Great. Perfect. So linkage is another very important class, and it's also probably one of the most complicated classes that we're going to have to end up implementing, because what it really does is it represents the calling convention. It actually is, it handles all the calling convention for function dispatch for both callers and callees. So anything to do with calling out or calling in, it's handled by the linkage class. So linkage itself is actually a concrete extensible class, but you can then derive by the different processor architectures, you can derive different linkages from that. So big example would be system linkage or C linkage, something like that. And it's basically all the rules that need to be followed in order to implement system linkage for that particular processor. You can also do things like in the case of Java, there's something, if you look at that code before in OpenJ9, There's like private linkage in that. So you can really build up your own kind of linkage here. And then it can get even more complicated like that. Like if you ever look at the Z, on the Z architecture and the Z code gen, they've got different kinds of system linkage depending upon the operating system that you're on, ZOS or Z Linux and that sort of thing. So things can actually get quite complicated. So the base class really describes the linkage properties. So things like, what order do you have to evaluate arguments? Do you do caller cleanup or caller stack cleanup, that sort of thing. It's responsible for generating the prologues and epilogues for a particular method. It has to map the arguments and the locals of a method onto the stack. So, buying the stack frame, figuring out how, like the order in which they should be mapped on there, inserting any kind of alignment you need, coming up with the actual offset of where that thing is so that the code can actually find it. So all kinds of things to do with that. It needs to handle the caller and callee frame building. So on the caller side, actually not really callee frame, but on the caller side, when you're going to be doing a call, like a dispatch, what do you need to do in order to build that frame to call some other function? And how do you get, like, which parameters are in registers, which parameters are passed on the stack, and how do they get there? And even things like if you've got something that splits, like if you've got something that's split between the stack and a register, how do you maintain that, and how do you pass, how do you handle varars and all that sort of thing? So it can be a fairly complicated class for sure, and it's usually one that will take a bit of care and a bit of time to get right. So I think that might be something that this may be one of the more complicated things that we have to work on for sure. So I guess for some lighter fare now. So you'll undoubtedly see if you start looking at other code generators and even the 32-bit ARM that there's sort of this notion of things called snippets. This is actually a fairly old concept. It's actually one of the very earliest means that we had in the code generator for handling sort of exceptional circumstances. So what it really is, it's an out-of-line sequence for handling these circumstances, and it's used for things like arithmetic overflow or stack overflow, or if you have to make some kind of a transition into the interpreter for some exceptional case. The way that we've traditionally done it is with something called a snippet, and they're mainly characterized by the fact that they are all hand-coded instructions, and that means that they're not register assigned. So if I need to create an instruction, I create it knowing that the source register is going to be GR2 and the target register is going to be GR8 and that kind of stuff. And they're actually emitted fairly late after the binary encoding. It's basically just like run through and write them out. It's actually a fairly, you can actually write some fairly compact code that way, and you know precisely what's going to happen. But these days, there's actually better ways of emitting code out of line. So these are sort of relegated to sort of, I guess you can say they're mostly deprecated in most architectures, but they are still used. It's just a fair bit of work to convert them into something new. So that's going to happen, hopefully over the next 5 years or so. But but they're there. You're going to see them. So the thing that most code generators use these days are things called out-of-line instructions. So this is where we actually create a secondary instruction stream that can be evaluated to, or you can add instructions to. And, it basically handles the exceptional code paths, but they actually provide a bit more power in the sense that you can actually evaluate a node on that stream, right? So I don't actually have to manually go through and insert instructions one at a time in a very precise encoding. I can just simply evaluate a node on that stream, and it'll create all the instructions it needs to do that. Where that's super useful is with calls, because if you didn't have the ability to evaluate a node that was a call out of line, and you wanted to do that call with a snippet, you would actually have to go and figure out the linkage, and you'd have to do every little step manually, which would be a very error-prone and very tedious process. So, so that's sort of what motivated these in the first place. They are register assigned. Most of the register assigner thing in the different architectures are smart enough to handle spilling that occurs like in the out-of-line path and not in the mainline path that will branch to it. So I said before that the register assigner isn't smart enough to handle control flow. This is kind of an exception to that, where we actually did have to add some exceptional code to be able to handle these out-of-line instructions. And they can branch back to the mainline code to carry on. So you can go on a line, do something unusual, and then go back again. Yeah, and basically the way they work is that once instruction selection is done, this sort of secondary instruction stream is just appended to the mainline one, and then everything just kind of gets assigned together, and the encoding all occurs together, and everything just kind of works. The one little gotcha with this is that the way that you determine the target, like determine where you're going to be evaluating your instructions, you have to do this programmatically, right? So you do this in CodeGen, and you basically have to say switch the instruction stream to either the mainline one or the out-of-line one. So you basically have to control where things are going. Not a big deal. Okay. And then the last thing I guess I wanted to mention was is the debug class. We have the debug story is we don't have the cleanest solution anymore. The API and there's a lot of reasons for that, but if you've ever looked in one of the debug classes on a particular in a code generator, you'll find that there's a lot of stuff in there. It's often hard to read. A lot of the functions look exactly the same in terms of their signature and that kind of thing. But it's all there for a reason. But we're going to have to provide one unless somebody goes and rewrites all the debug code in the meantime, which is not likely to happen. So basically what we have to be able to provide are architecture-specific implementations for things, for printing instructions and registers and snippets and any sort of architecture-specific stuff we have to be able to provide, the means of doing it. And that's not such a big deal, but it's just a little bit tedious to do, and the API isn't great. We've actually deprecated the API. We don't really want to start adding a lot of stuff onto this debug API. We do know that it needs to get re-architected at some point. It's just unfortunately just not the it's just not that high on the priority list anymore. So okay. So I think that's my last slide. Yeah. So that's basically the talk that I wanted to have today. I'm happy for you guys to have questions or whatever. If I've missed something, or if you want deeper clarification on something, I'm happy to provide that. I guess if your mics don't work, I guess I can take questions through the chat if you have them. Try that again. I think Kono-san just find. Oh. So Kono-san was saying that the ARM32 debug code was no longer used, and you removed from the code repository. Okay, that's interesting. I guess I'm somewhat surprised to hear that, because ultimately it's still going to have to. I mean, there must be other means that it uses for printing instructions, for example, or knowing how to describe how to print the registers in a memory reference and that kind of stuff. So I haven't really explored that too much on ARM, but Okay, so if there's no other questions, so in terms of next, so James asking, how do jumps work? Does it take multiple passes to figure out the distance needed to jump? So, so there is a, right, so the way that we handle branches and where they need to go is with what we call relocations. And relocation processing is actually, so as you're generating instructions, when you need to generate the target of a branch, you end up creating a relocation for it on that pass. And then there's a separate pass on relocation processing to really figure out what the actual address of that target is, and then potentially fix up that instruction to branch to that label. So relocation processing is the thing that accomplishes that. If you look at relocation processing, it's actually fairly complicated. It's a lot more complicated than you might think it should be. And the reason for that is because it does more than just sort of the branch relocations. It also does a lot of the stuff for ahead of time compilation as well, where there's other parts of the code that need to have relocations associated with them. So it looks a little bit more busy than it perhaps actually is. So. Any other questions? So, so if not, I think the next step here is, so I guess two things. So one is I would like to sort of establish a regular cadence of calls now where we don't just, where hopefully we can make it more, more interactive. I'm thinking the best day for this is going to be on Wednesdays at around, I think, 6 p.m. Eastern. I'll have to check on that, just make sure everyone's okay with that. But the next step I think we need to take here is to sort of, because we've got a lot of different people here, and there's potentially a lot of overlap in some of the work that we need to do here. I think what I'll do is just take some of the experience that I have and sort of carve off pieces that I think can be done independently, and then we can all discuss about who's going to do what work, so that we don't end up stepping on each other's toes. Because, like, for example, we all can't work on the linkage class at the same time, or we all can't do, something at the same time. And there's also key infrastructural pieces that need to be built first, right? Like, for example, start building up the code generator class. The machine class is very important, right? So the very important things like that to provide some of the mechanisms that we're going to need to be developed as well. So, so I think what I'm going to do next is to kind of go through and at least put some thoughts down as to what the different independent pieces are and how they can be worked on, and then we as a group need to decide on who's going to do what, and kind of go from there. So I'll just pause there for a sec in case anybody wants to ask a question in the chat. But if not, I think we can adjourn. Just hang on a sec. Okay. All right, so I've recorded this, so I'm going to post it up on our Eclipse OMR YouTube channel in case anyone who didn't get to hear me get through this wants to hear this. I'm hoping that in the future we can drill down in much greater depth on some of these other topics. For example, register assignments, or even the relocation processing, that kind of stuff, or metadata generation, whatever. So. But for now, I think that's it. So thanks everyone for joining, and I'll talk to you again soon. Bye.
Bye.